Welcome back to the course Modeling Combustion with ANSYS Fluent offered by Adal Systems. So in today's class we will discuss about species transport model. So let's begin the class. Introduction to species transport model. This model is simple and it is widely used for solving reacting flows. The reason is it solves conservative equations of convection, diffusion and reaction sources for each component species. In species transport, we can add mixture materials which will specify a set of species to be included in the model. So some of the key features of this model are as follows. Mixing and transport of chemical species can be done using this model. Then various chemical reactions like volumetric, which happens in bulk, volume, then wall surface reaction, particle surface reaction, etc. These reactions can be modeled simultaneously. While defining mixture material, we can add up to 500 different chemical species using this model. One of the most important feature of this model is that turbulence chemistry interaction has been focused and 4 different models have been embedded in species transport. So based on the problem definition, one can go with the turbulence chemistry interaction model. Also, there are some of disadvantages using this model, and they are when mixing and kinetic time scales are comparable, this model becomes unreliable. Also, it is difficult in determining intermediate species and dissociation effects. Now we will see what all are the steps involved when we are dealing with species transport model. So these are some of the steps which we gonna follow, and we will discuss each of them in further slides. So the first step, that is enabling species transport model. After enabling viscous model and energy model, we have to go into species and we have to enable the species transport model. Then we can select what kind of reactions we want to include in our model, and there are other options also one can go through. Next important step is defining the mixture material. Various fuel oxidizer combination mixtures are already embedded in Fluent, which one can go and select. One of the example is methane and air. Select the template and then go on. Otherwise, one can create their own template using different combinations of fuel and oxidizer. So after selecting the flame, next step comes is defining the properties for this mixture and its constituent species. You can individually go and change properties of methane as well as air and for the overall mixture as well. So the third step is to define cell zone conditions and boundary conditions for the species. We have to give boundary conditions for this species. So we have to give mass fraction of fuel as well as mass fraction of oxidizer at all the inlets. For inlets, at what mass fraction of fuel and oxidizer it will be entering the domain in one condition, that is addition of mass fractions of fuel and oxidizer should always be equal to 1. At walls, the default is 0 gradient boundary condition. One can go and change it also according to the problem. And for very small inlet velocities, inlet diffusion can also be defined. Next is defining any other chemical source terms, because there may be a case when species sources exist in your problem but you don't want to model them throughout the mechanism of chemical reaction. So you can add them as source or sink of a chemical species within the computational domain using this option. So next it comes to fifth step, that is solution procedure. So while dealing with combustion problem, there may arise some difficulties because many species and chemical reactions are involved when we are dealing with a combustion problem. So there will be a stability and convergence problem. So some solution procedures, they involve it by changing some of the under relaxation factors. One step which many of the people follow is two-step solution procedure, that is without energy equation, cold flow analysis will be done, then continuing the same simulation, then hot flow analysis will be done with enabling the energy equation. One can vary the density under relaxation factor because when combustion is involved, the local temperature value which it reaches is very high and then it may lead to divergence. But at that time one can alter the density under relaxation. Also in a reacting flow, ignition can be defined using batch or a spark model which is already present. So these are some of the solution procedures. After everything is done, post processing has to be done. So for post processing, various mass fraction, mole fraction, molar concentration for each individual species can be calculated and can be seen through various plots, profiles, etc. in ANSYS Fluent. One more thing which we can do is, Chemkin is one of the product of ANSYS in which complete chemical kinetic analysis can be done. So one can import their mixture material in Chemkin and carry out the analysis, and then it can be imported back to ANSYS Fluent and a combustion problem can also be solved. So So now we will see a demonstration of an example using species transport model where we will see how we can pre-process our simulation using ANSYS Fluent. So let's begin. So here we will discuss step-by-step procedure for species transport model with an example. So here I'm using ANSYS 2020 R1 for this demonstration. So I have already imported the mesh here which we can see. So we will begin the procedure. So one of the important step after importing a mesh is that we need to check the quality. So we'll press check. So there are no errors. We can proceed forward. Next is the report quality. Even the quality which we are using is very good. Then we can go to type. We have to select which solver which we want to use, pressure based or density. So here we'll be using pressure based. Also we'll be simulating steady state simulation. So in time we have to select steady. Then 2D space is planar and velocity formulation we are using is absolute. For this simulation we don't want to include any gravity effect, so we have not used the gravity here. Next we will go to models. So after going to models we are dealing a combustion problem, so we have to enable the energy equation. We are enabling. Then we will go into viscous. We need to select the turbulence model. So here by default K omega is enabled. So we'll go with the K omega model here. Then after selecting a turbulence model, we have to go and we have to specify our species model. So in species, it is an off condition. We have to select the species transport model. So in species transport, we have to select the type of reaction. So we're going to simulate volumetric, that is bulk reaction. So we will enable the volumetric here. Then we can see there are various options also, that is wall surface, particle surface, electrochemical. So based on the problem definition which we are dealing, we can select any of the reaction types here. Next, we have this chemistry solver which we can select out of the 4. So here we don't need for this simulation. We will select the explicit source. Then for other options like inlet diffusion energy source, based on your problem you can select. So here we don't want to use any of these options. Next, into the mixture properties. The mixture here is the reactants which you want to simulate, that is the chemical species which you want to import into the species transport. We can select from the mixture template. So in mixture template, there are various options, various combinations have been already showcased in ANSYS Fluent. So here for today's simulation, we will use kerosene air mixture. So we have selected kerosene air from here. Then we can go into view. And we can check several options available for this model. So mixture species, we'll go to view. So these all species, 5 species are included, that is kerosene, the oxygen, that is O2, N2 is also into reactants, then CO2 and H2O. So these all chemical species are included in the kerosene air mixture template. Then here in reaction, there are 3 different reactions out of which we can select one. We will discuss it how we can select these options. Then we can also import a Chemkin mechanism using this option. Right now we don't want to import any Chemkin mechanism. Then number of volumetric species here which we are having is 5. We have seen the kerosene, O2, N2, CO2 and H2O. So these 5 chemical species, volumetric species, will be modeled in the simulation. Turbulence chemistry interaction models, as we discussed in our presentation, have 4 different models, 4 variety of models. So the first option here, finite rate or no TCI, that is no turbulence chemistry interaction. So basically this type of model we can use for laminar flows, and the rest all 3 we can use for turbulent flows. So for this simulation we will use eddy dissipation model. Also we can do Cole calculation here, but our simulation don't include any Cole calculations, so we won't be using this option now. Then select boundary species and select reported residue. These are options, if we don't even select, then it is fine, because they are very model specific options which we are not going to deal with. And we will go to apply. So the model has been applied, then we will just click OK. So after enabling this model, we can see various things have been changed in our console. It is adjusting the following settings. The Fluent will automatically adjust some of the settings based on the problem we define. So the reaction method has been changed to eddy dissipation, it is showing. In species transport, there are these other options which we can use, that is NOx formation. One can, if one want to simulate NOx formation in a species model, then they can select the option of NOx and then specify the various things they have provided here. So right now we don't want to use. Then SOX is also there, soot formation is there. So these different options are being given with species transport model. So we don't want to use these options. Then we will go to materials. In materials, what chemical species we are enabling, that is what reactants we're going to use. These all reactants, in their chemical forms with their certain properties are shown in materials page. Then we will go to mixture. In here we can see in material type, if we select mixture, And in fluent mixture materials, if we select kerosene air, which is already selected, we can see various options are present. If we go to mixture species, then we can add or remove any of the species which are already included in the kerosene air mixture. So this option is available. Then into reaction, now we have selected the edit dissipation reaction. So we can edit this the way we want. So here we can see to the right of this page, we have number of products, that is 2 products. The products will be CO2 and H2O. And then to the left we have the number of reactants, that is 2 reactants, the kerosene and the O2. So here you can specify the stoichiometric coefficients and the rate exponents for this reaction. Also you can provide the mixing rate. So these all standard values are found in the combustion handbooks. One can refer combustion handbook and can give these properties according to their need. Click OK. So the reactions has been specified now. We will go to mechanisms. In mechanisms, there is this one option. If we want to go and we can also edit this option. But the one which is default, we can go with the same. Then for this entire mixture, we can select what kind of density formulation should be used. So the default here is incompressible ideal gas. So we will proceed with incompressible ideal gas. Also, we can select some different method how we want to solve our density equations from the following. Then we can also change how we want to solve our specific heat, that is Cp, with the following options. Then just like same, there are several other properties which we can change accordingly how we want to change them. So this is for mixture. Then we can go to fluid, and then we can change individual properties of some of the species. Like if I select oxygen, then I can change some of the properties of oxygen. Same we can do with any other species. Like if I select the kerosene which we are using, we can change these properties according to our need. Also, we can add some new species from this Fluent database. So here we can see that kerosene air mixture is selected. So same way we can add some different, like if we want to add this benzene air mixture, we just have to click and then we have to copy. So now we don't want to use it, so I'll just close this window. Then after settling everything, we just have to click on change create. So once the change create is done, we need to close this material. So in mixture we have these all species. For fluid we have air, and for solid we have aluminium. So the materials are defined now. So now we have to define the cell zone conditions. So zone is the region where we have to specify the properties in bulk. So I'll just change it to zone type. So this zone 2D tube is fluid zone. So if I go change to edit, here we can see there are various options which we can do. Here we can change the fluid we are using are 2 fluids now. The kerosene air mixture which is present is in fluid form. Also the air is present in fluid form. So we can give frame motion, we can give porous zone, laminar zone, source term, etc. So if I select the source term, can go into source term, and then we can give the number of sources. Like if we have to specify any energy source, then we can give and change this options accordingly. So I'll just off this source term, and then we'll go to OK, because we don't want to change anything here. Just go and click OK. So the cell zone conditions are defined. Now the main thing which we want to specify is the boundary conditions. So as we see from the steps that we have to specify species, mixture fraction, mole mixture fraction, etc. We will see how we can specify that. So here inlet which we are going to specify is velocity inlet. So we'll go to velocity inlet and click edit. We can change certain properties, we can add certain values here. So for velocity, we can see the velocity specification method is magnitude, that is normal to boundary, and reference frame is absolute. We can directly specify the velocity magnitude here in meter per second. So I'll specify 60 meter per second velocity here, and the supersonic initial gauge pressure, that is in Pascal, that will be 0. Then for here we will, for turbulence calculations, we will go with the default values. Then in thermal tab, we have to specify the inlet temperature. So 650 will be our inlet temperature. Next in species, we have to specify species in mole fraction. So here for this simulation, we are dealing with 0.8 equivalence ratio. Just for this simple case I have taken. So based on the chemical reaction, the moles are calculated. So when we write a kerosene air mixture chemical reaction, we will automatically get for 0.8 how much moles of kerosene and how much moles of oxygen is needed for the chemical reaction to take place. So according to the calculations, the mole fraction of kerosene needed for 0.8 equivalence ratio is 0.01169 and for oxygen it is 0.20762. So everything is specified. We will go to OK. So we have specified our boundary species. Then outlet is pressure outlet. We will be using pressure outlet here. We'll go to edit. Then for pressure outlet, we don't have to change much of the properties here. Thermal, it will be 300. Species, we don't have to specify here because it is outlet. Outlet, it has to be calculated. So we'll just go with OK. Then walls, it is nothing. We will just check what else we can change for wall. So here in walls, there are several conditions. That is, if you want to specify that is wall is moving or wall is stationary, then shear conditions, that is no slip condition. Then in thermal tab, we can specify different thermal conditions, that is if it is having a heat flux, then convection, radiation, mixed up, etc. In species, we can go and we can do some of the modifications, but as of for now, we don't want to use anything. We'll go to OK. So everything has been specified, the boundary conditions are placed. We will just check operating conditions. The operating pressure Pascal, it is the one which we want to use, then we'll click OK. The rest of things which are present here in setup, we won't be using much of them here. We'll just go to solution methods. In solution methods, it is coupled. We will go with the default values, but it is a better practice to change the upwind scheme methods to second order. So we'll just change this one. So restore our second order. Then we will go to controls. And we don't want to specify any of the under relaxation factors as of now. So these are the default under relaxation factors. So we can see here in equations, if we select, then here we can see that these all 7 equations will be solved when we start the simulation. So from here we can select which equation we don't want to solve. That is, we don't want any of the species equation to be solved. Then we can off them. We can just click them and they won't be solving. So as of now, we will be running for all the 7 terms. So we will click OK. So these all properties will be calculated. So these are the under relaxation factors for the same. Also, we can change the limits for the solver. That is, we can change some of the limits according to our problem if we are facing any divergence. So we'll just click OK. Then there are some advanced settings and everything. We can go for it. This was all about the solution controls. In report definitions, this is used for post-processing purposes. So we can create a report file or a report for any of the properties. So we can create a surface report, volume report, force report, then flux report, and etc. So we can define any parameter which is not present in Fluent using user-defined function. So we'll just close this one. Right now we don't want to specify anything. Then we can give monitors, that is solution monitors. Here we can plot residuals. We can change some residual settings also here. It is for each of the equation how we want to see. That is, a monitor will be there. Then check for the convergence. Then the absolute convergence criteria is given here. We can also modify this according to our needs. So I'll just go with OK. Then we can see report files, report plots, convergence criteria, etc. Then here is cell registers option. So next is the solution initialization. Here 2 types of initializations are present, that is hybrid, which will be done by the system. We don't have to specify anything. In standard hybridization, we can select that from where we need to compute our results, that is from where we need to start our solution. So for our simulation, we'll be starting with the inlet. So we will initialize everything from inlet and the reference frame will be absolute. So once we change this compute from inlet, we can see how these properties have been come to the place. That is inlet velocity which we have specified, that is 60 meter per second is the x component, and based on that value the y component has been calculated based on the area of the inlet. Then we can see the turbulent kinetic energy is also calculated and specific dissipation rate, that is the k omega value which we see in a turbulence model. These things have been calculated, that is initialized. Then the species mole fraction which we specified at inlet boundary condition and the temperature. So we will initialize this solution. So the solution has been initialized. Once the solution has been initialized, we can see some other options are also enabled, that is the batch and the species. So right now we won't be using this batch option or the species option. We will go straight to calculation activities. So here in calculation activities, we can specify the autosave entry, that is after how many iterations a data file, that is the solution file, should be saved. So we can go into edit and we can specify all these values here. We can give the path where we need to save our data files. So we won't be using this option right now. Then we can go into run calculations and then we can see for this check case option. It will tell us that are any further recommendations needed or are there any changes we need to make for the case which we are creating or the solution which we want to run. So it is saying that no recommendations to make at this time. So everything is properly done. Then we will give the number of iterations we need to solve. So for this simulation, I will just go with 30 number of iterations just to run it fast. Here in data file quantities, which mostly are used for the post processing purpose in CFD post. So these are the standard quantities which are stored in a data file once the solution is generated. We can also add other properties which are not present in the standard quantities from this right side table. So there are various factors which we need to add. So for the species model here, we can see several species options are present. There is mass fraction, molar fraction, then laminar diffusion coefficient, enthalpy, etc. So we can add any of the quantities from this side. So they will be added to the data file quantities which you want to see after the solution is done. So I'll just click on present and everything is done. That is 30 number of iterations are being specified. Then we have to do is that we have to go to file, we have to say write and write case. So we need to save this as a case. So I'll just save in the course folder. Then we have to click OK. So the case will be saved in console. We can see the process is done and then we can go for calculate. So once we click the calculate button, we will see how the solution gets started and how the real-time solving we can see in the display view, and each equation solving we can see in console how the residuals is getting converging. So we'll just click on calculate. The solution is completed now. We'll just click OK. Then we will go again to file, write, data. Make sure you save your data where you have saved your case file. It is better. We'll click OK. So the data file is getting saved. So the next part where it comes is the post processing. So some of the basic post processing I will show you in this class. So just close this all pre-processing things and we will go to results. So here in results we can see there is this graphics option. In graphics we have to select contours. In contours we have here several options which we want to see. I will just select the velocity, velocity magnitude, and we will go for scale display. So it will show me a velocity contour. So this velocity contour is for the entire 2D plane which we are using. Then we can go and we can change it for temperature. So temperature we are saying now static temperature. We will go to save display. We can see how chemical reactions are started in the domain. We can change and we can see for total temperature as well. So total temperature and static temperature won't be much difference here. And we can change and see various options present here. So right now I won't be changing this one. Here we can see the minimum and maximum are fixed according to the scale which we have provided. We can also change this option. We need to off this, then we can change this value according to our need. It is better practice to go with the auto range because we don't know exactly how much the values it has touched. Then we can add new surface. For 2D we can add line, quad, isosurface, isoclip, etc. So the plots which we do, the XY plots, they are plotted at lines and not planes. So we can construct those lines with this option here. Then once a contour is plotted, we can save this contour from file and save picture. So in save picture we can select what format we need, what coloring we need, then file type, resolution. We can change this resolution according to our need. And then we can save this. So once the contours are done, we can go to other post-processing factors, that is vectors. So vectors are very important when we are dealing with swirl combustion. So we will see how this velocity vector works. So I won't select any surface here. First we will see how it is there for the entire domain. Okay, so here we can clearly see, if we just zoom in. So after zooming we can see that the arrows are pointing outwards. So we can use this velocity vectors for such swirl kind of combustion, but right now we are using a simple straight flow combustion. So all the arrows, they are pointing towards the outlet, that is air is entering from inlet and it is moving towards the outlet. Also the boundary layer is formed at the walls you can see clearly how the velocity is changing at the walls, at the wall locations. We can also change the scale and slip of the vectors, and we can make it bulky or light according to our need, how we want to visualize the flow. According to that need, we can proceed forward. Also, we can save the same vectors how we saved the contours with the save picture option. Then I'll just close this one. Then we can go for the path lines also. So in path lines, we can see the path of the flow, how the flow is moving in a simulation. So here we have to specify the variable which we want to see. We'll go with the velocity magnitude, and from which surface we need to see. So I'll select inlet. Then we have to pulse. It will start. So we can see how the path lines are moving in one direction, that is they are moving from inlet to outlet. We can see a small curve is happening at the walls, and in between as well the boundary layer is forming as it is moving towards the outlet. So we can save this one as well. I'll just stop this one. We can go for save display as well. In this pathline options, we can change what kind of style we need. So here we are using line. We can change this to sphere, we can change this to triangle, ribbon, etc. How we need to visualize the results. So I'll close this window. Next we will see reports. So in reports we have several options, that is forces, projected area, surface integral, volume integral, etc. So if we select a surface integral, we can see any particular thing which we want to check. So I will select mass weighted average. In mass weighted average, I'll select pressure, and any one location we have to select. At that one location we can compute what is the mass weighted average pressure, the static pressure. I'll click on compute, and at inlet we can see that this is the static pressure it has maintained. Then if I change this pressure value to velocity, we can check for the velocity as well. So inlet we have specified a velocity of 60 meter per second. So we can see it has taken 60 correctly. And for outlet, if we calculate, then we can see the velocity has been increased to 89.47511 from 60 meter per second. The same way we can check each and every parameter here. So for temperature we will see that for outlet it has taken 650, but at outlet we can see how much it has been taken, that is how much it has computed. The temperature has been gone to 970 Kelvin. Also we can see that in console we have values displayed. So we can save these values as well. We just have to go to right, you have to give right, and then you have to specify the path where we want to save the file. Then I'll close this window. Same way we can do with volume integrals, and also we can do with forces as well. Forces and fluxes, we can calculate these all reports at particular definitions for some particular variable. One thing I forgot is the plots. So in plots we can plot an XY plot, histogram, data sources, profiles, etc. So for XY plot, if I select, then we have to change this axis option. So x-axis I will put 0, and for a wall, that is for y we need to see. So x will be 0 and y will be 1. So we will see for velocity how velocity has increased. So this velocity we will see at an inlet, how it has changed. Here we can see that velocity value. So for y equals to 1, we can see how the velocity has been maintained 60 at the inlet. The same we can see for outlet as well. So we can compare how the velocity has changed. So if we see with the legend, we can check here. So with the legend we can check here that how velocity is different for the inlet and the outlet. Velocity has increased from 60 to the 89 meter per second. So also here we can write this file as an XY plot file, so we can plot it in Excel for further post processing. So I'll click on write, and then again we have to specify the path where we want to save it and the name, so we can access the file next time. So I'll just off it. Same way we can check for several other parameters as well. So I will go with the temperature as well. You will see how the temperature is varying for the inlet and outlet conditions. So this way we can plot an XY plot. Then it is histogram. For histogram we can see the same things. So I will change this to velocity again, and we have to specify inlet plot. So this is how the velocity is changing at inlet. Then there is this parameters and customization. So one can change the parameters how they want to change and do some customization how they need to do. One more thing I forgot to check in post processing is that for species values we will see contours, how the species is changing. So we have to go into species, then we have to see mass fraction, or anything we can take, mass fraction, mole fraction. So I will see mole fraction, how it is changing for the fuel. So here we can see that at walls the reactions is happening. So the fuel which is entering through inlet, how it is getting consumed near the walls and how the reaction is taking place. We will see for the products as well. CO2 I will check first. For CO2, we can see that how the CO2 is forming at the walls just where the fuel is getting consumed. So this way we can model a combustion problem in species transport using ANSYS Fluent. So summary of today's class. So we learned that species transport is simple model which is widely used for solving reacting flows because conservative equations of convection, diffusion and reaction species for each components are solved here. Then mixture materials can be added, which is a very good thing. Then we saw some of the key features of the model that various simultaneous chemical reactions are solved. Then we saw some disadvantages where we got to know how the model becomes unreliable on some certain conditions. At last, we have seen some steps how we can model a combustion problem using species transport of ANSYS Fluent with a demo example. So the references for today's class are present here. In next class, we will start with non-premixed combustion model. Thank you.